Good evening to dear participants. A warm welcome to today's session, day 3, 5 and 6. So it's my pleasure to invite Dr. Naveen Reddy T to introduce our esteemed resource person, Dr. B. Anantha Lakshmi, for the session 5.
Thank
Sir,
you.
over
Thank
to
you.
you, sir.
Thank you, madam. Good evening, participants and dignitaries and fellow colleagues. Okay, welcome to the day 3 of our FTP program. I'm very happy to introduce today's our speaker, Dr. Anantha Lakshmi. Madam, Dr. Anantha Lakshmi, madam, currently serving as a research assistant professor in Gachon University, South Korea. She also completed a PhD from the same university in the field of material science and nanotechnology. Um, she completed B Pharmacy and M Pharmacy from Andhra University, and she has contributed good journals, about 17 high impact factor journals towards life sciences. Uh, and additionally, she also have acquired the Research Excellence Award from South Korea, and also Pratibha Gold Medal Award from Government of Andhra Pradesh. Okay, with this introduction, I will hand over the session to Madam. Madam, this session is yours, Madam. Dr. B. Lakshmi, Madam. Thank you, Madam.
Yeah, welcome, Madam, Dr. B. Anantha Lakshmi. So let's start the session.
Hello. Uh, thank you. Thank you so much to the faculty team and Dr. Naveen Reddy garu, and Dr. Saraswati ma'am, and to the whole management for inviting me to deliver this session. Is my voice audible, ma'am?
Yeah, it's
Yes, ma'am.
audible,
Yes.
madam.
Okay. And so the topic which I am going to deliver today is I want to share my presentation. Ma'am, is it visible?
Yes, ma'am.
Okay.
Yes, it is visible and
Okay. Uh, my topic name is Real-Time Challenges in Water Purification. Just a second, ma'am. Mm. Oh, is it visible, ma'am?
yes, ma'am, it is visible.
But for me, it is not showing. Just a second, ma'am.
Yes,
Sorry for the interruption.
Yeah,
madam.
no problem.
Okay. My topic name is Real-Time Challenges in Water Purification and Contaminant Monitoring using Photocatalytic Nanomaterials. This is the outline of my topic, which consists of introduction and what is water purification and the challenges and the advantages of using photocatalytic nanomaterials and the future scope. Coming to the introduction, we all know about water. Generally, water is a transparent fluid and the molecular formula is H2O. Majorly, it exists in liquid state, also coexist in solid and also gaseous state. And it covers almost 71% of the Earth's surface. The density is 997 kg per meter cube, and the molar mass is 18.01528 grams per mole. And the boiling point is 100 degrees centigrade. Melting and freezing point is 0 degrees centigrade. And it is a polar molecule. Most of the uh, Mostly it is used as a solvent and also known as universal solvent. It dissolves so many substances, and the pure water is tasteless and also odorless. Uh, on the earth, all known forms of life depends on water, and generally water cycle, we all know it. It includes precipitation, transpiration, evaporation, condensation. These are the means of modes which we depend on water. Um, Generally, water is polluted through many ways, like natural ways with floods or cyclones, and also man-made. Man-made water pollution is the major source of water pollution. It includes like urbanization, industrialization, etc. The source of pollutions includes sewage, industrial and trade wastes, and agricultural pollutants. So, water pollution includes like groundwater pollution and surface water pollution. And in the figure, we can see which types of pollution is present in groundwater pollution and surface water pollution. And indicators of water pollution includes total suspended solids, biochemical oxygen demand, and concentration of chlorides, nitrogen, and phosphorus. Generally, the biologic biochemical oxygen demand means the amount of oxygen required by the bacteria to decompose the uh, organic decomposition. And there is chemical oxygen demand. In this, both degradable and it degrades both biodegradable and non-biodegradable substances. Generally, through this water pollution, humans are suffering with many water-related diseases like viral, bacterial, protozoal, and etc. Uh, Generally, these include chemicals. This chemical pollution is mostly the main source of water pollution, and also dental, oxidative stress, inflammation, and cyanosis in infants. Many cardiovascular diseases is caused by this water pollution, and endocrine disruption due to chemicals like phthalates, atherosclerosis due to microplastics, etc. This water purification, uh, it is the process of removing undesirable chemicals, biological contaminants, suspended solids, and gases from the contaminated water. Generally, mostly diseases are caused by the pathogens like bacteria, viruses, and protozoa. And also the chemicals toxic chemicals like lead, arsenic, fluoride, and nitrates causes most of the diseases. In water, most of the suspended solids affects the clarity and also taste of the water. Drinking such water can lead to serious health issues, including GI infections, neurological disorders, and developmental problems, especially in children. So, water purification is necessary for human health. Generally, the purification of water includes many ways like natural purification and artificial purification. In natural purification, the techniques includes aeration, sedimentation through sunlight, dilution, oxidation, and through plant and animals. Uh, Generally, in rural and urban areas, we are using artificial purification process, which include physical process, chemical process, biological process, and electromagnetic radiation. Physical process generally includes 4 types of methods, like infiltration process. The major solid particles in a liquid are removed by using a filter medium that permits the fluid to pass through but retains the solid particles. But the water would be filtrated. In the sedimentation process, this process includes the the sedimented particles are removed from the water by means of gravity or separation. And the other physical process includes distillation. It is the purification process where contaminated water is heated to form steam, which is then cooled and condensed back into liquid form, leaving behind the impurities like inorganic compounds and microorganisms. The other process of physical process include reverse osmosis, the process that uses high pressure to force water through a semi-permeable membrane, effectively separating and removing contaminants like dissolved salts, heavy metals, bacteria, and viruses to produce purified or permeate water. And coming to the chemical process, in chemical process, the steps will be like flocculation, a process that forms large clumps or flocs from smaller suspended particles in a liquid, allowing them to be separated more easily. And the other one includes chlorination. It is the process of treating water by adding chlorine or chlorine compounds to disinfect by killing harmful microorganisms such as bacteria, viruses, and other microbes. Coming to the biological process generally uses microorganisms to break down organic pollutants and nutrients in water, converting them into less harmful substances through processes like activated sludge, biofiltration, and anaerobic digestion. Microorganism consumption. These microorganisms such as bacteria, fungi, and other microbes acts as biocatalysts to consume the organic matter and nutrients in the water. The breakdown and transformation of this process includes these pollutants they use for food. The microorganisms break down complex organic molecules into simpler, less harmful substances, like carbon dioxide and water. The two types of process including in this biological method are aerobic process and anaerobic process. In aerobic process, this method requires the presence of oxygen. Example include activated sludge system, where water is mixed with microorganisms in a tank to consume organic matter and biofiltration. These microorganisms grows on filter media to transform the contaminants. And in anaerobic process, in this system, substances other than oxygen can act as the electron acceptor, allowing for the breakdown of organic matter. And the separation and disposal process, in this one, after the biological treatment stage, a clarifier separates the treated water from the solid microorganisms and other particles. A portion of these microorganisms may be returned to the process while the rest is removed for disposal. The other method used for water purification is electromagnetic radiation. In this method, they uses ultraviolet treatment. In this method, ultraviolet light can be ranging from some frequency of the wavelength is used to inactivate pathogens like bacteria, viruses, and protozoa in water. The method which includes in this can occur in the mechanism by damaging their DNA, preventing them from reproducing and causing illness. This chemical-free process is effective for clear water and does not alter the water's taste or smell, and it requires minimal maintenance, though its effectiveness depends on the water's clarity and can only treat contaminants at the point of contact. The wavelength of the UV light generally used for this method can be around 254 nanometers. This wavelength can penetrate the cells of the microorganisms and causes DNA damage. This UV radiation generally damages the genetic material like DNA or RNA. So, after damaging the DNA or RNA, it will the ability of the reproducibility will be minimized. After that, the inactivation step comes by rendering the pathogens to unable to reproduce. The UV system effectively disinfects the water. Among all these processes, generally there are challenges in water purification. The difficulties arise from the dynamic nature of water sources, the need for continuous oversight, and the cost of deploying advanced solutions. So we need to monitor these challenges. In this, some challenges I have presented here. They are like labor-intensive processes. Traditional water quality monitoring relies on manual sampling and laboratory testing, which is time-consuming and labor-intensive. This approach cannot provide the immediate data needed to respond to sudden contamination events. And the sensor limitations in this, the smart sensors are being deployed. Challenges with their performance remain. Concerns include the sensor's accuracy, robustness, and reliability, as well as their interoperability reliability, and security. Coming to the data standardization and access, ensuring the monitoring data is standardized and accessible across different systems is an ongoing challenge. The enormous volume of data collected by real-time monitoring systems also require a robust management system. Coming to the technical and operational challenges, first one is adaptive control. Water quality can change rapidly and unpredictably due to environmental conditions, accidental contamination, or infrastructure failure. Traditional systems have difficulty adapting to these sudden variations, required advanced AI-driven feedback loops to maintain stable performance. And coming to energy consumption, many water and wastewater treatment methods are energy intensive, especially for processes like aeration and sludge treatment. Optimizing energy use in real time requires balancing treatment effectiveness with power consumption. Membrane fouling and scaling. For systems using filtration, membrane fouling and scaling are common problems that degrade performance over time. Preventing these issues in real time requires sophisticated monitoring and automated maintenance. Coming to contamination events, effectively detecting and responding to intentional or unintentional contamination in water distribution systems is a significant challenge. Integrated monitoring and supervisory control and data acquisition systems are used to provide security alarms but require constant vigilance. Coming to contaminant specific challenges, it includes like pathogen detection and consisting emerging contaminants. Pathogen detection, the presence of pathogenic microorganisms which often enter water sources through human and animal feces. It is the major public health concern. Real-time systems need to detect these fast-acting threats immediately to prevent gastrointestinal diseases. Emerging contaminants, mostly new and complex contaminants such as industrial chemicals and pharmaceuticals, are constantly entering the water resources. So, developing real time technologies to detect and remove these substances is a significant challenge for modern water treatment. And coming to economic and infrastructure challenges, it includes the cost of implementation. Implementing a new AI-enabled systems with sensors, IoT devices, and other advanced infrastructure requires significantly financial investment. This can be a barrier for many utilities, especially in low-income or rural areas. And it also includes aging infrastructure. Many regions have aging water infrastructure, including pipes and treatment facilities, which can lead to contamination and leakage. Monitoring and mitigating these problems in real time is difficult when the underlying infrastructure is unreliable. Coming to cybersecurity risks, as water systems become more digitalized and connected, they also become vulnerable to cyber attacks. Protecting these systems from malicious interference is paramount to ensuring the safety of the water supply. And coming to personal skills, there is a need for skilled personnel who can manage and interpret the large amounts of data generated by advanced real time systems. Training and retaining qualified staff can be also a challenge. Coming to the other method of water purification is using nanomaterials and also the process of photocatalysis. Generally, in this method, it uses semiconductor materials like titanium dioxide and graphitic carbon nitride. It to degrade the contaminants like dyes, pesticides, antibiotics, and pathogens using light, typically from the sun. It can also be used through UV light. This process relies on advanced oxidation to break down the pollutants into harmless substances such as water and carbon dioxide. So, this method is generally known as green technology because it offers a chemical free and sustainable method for treating the wastewater and purifying drinking water, with researchers focusing on developing effective low cost photocatalytic materials and reactor designs. Coming to the history of photocatalysis, in the late 19th and early 20th centuries, scientists like Alexander Stolitow and Ferdinand Braun conducted experiments on the photoconductivity of selenium and other materials, laying to the groundwork of for future photocatalytic research. These scientists contributed to the understanding of the relationship between light absorption and chemical reactions in solid state materials. In 1972, the discovery of photocatalysis was published in British science journal Nature. Photocatalysis gained significant momentum in the mid 20th century with the development of semiconductor photocatalysis. Dr. Ichinos of Saga Ceramics Research Laboratory succeeded in manufacturing water-soluble titanium dioxide. Coming to the principle on how it works, it mainly uses light absorption. The semiconductor photocatalyst absorbs light energy, which excites electrons from its valence bond to its conduction band. So the reactive oxygen species formation occurs. Here the excitation creates electron-hole pairs. The electrons and holes then migrate to the catalyst surface where they react with water and oxygen to form highly reactive species like hydroxyl radicals and superoxides, so that the free radical formation will be occurred. These reactive species are powerful oxidants that attack and break down the organic pollutants, microorganisms, and other contaminants into simpler, less harmful compounds. Coming to the catalyst regeneration, after the reaction, the photocatalyst is regenerated and it can be used repeatedly. The benefits of this photocatalysis in wastewater treatment will be like used for effective pollutant removal. It can degrade a wide range of pollutants, including organic dyes, pharmaceuticals, pesticides, and antibiotics. And this method is generally used for disinfection, providing the chemical free method for sterilizing water, eliminating bacteria, viruses, and fungi. And also, this technology is uh, known as greener technology because of environmental friendliness. And coming to the cost, it is cost effective method compared to the conventional methods, and it can be more sustainable and potentially lower cost solution, particularly for remote or low power applications. And also it doesn't create secondary pollutants, like no secondary pollution. The catalyst is not consumed during the reaction and can be reused, and the process generally doesn't produce harmful byproducts. So why only semiconductors are used? But in this in this method, we can use metals and also non-metals. In metals, no band gap is present and only oxidation or reduction method is used. In non-metals, there is a wide band gap and it requires high energy. But in semiconductors, it can be used, the semiconductors can use UV light or also visible light, and it is suitable for redox reactions. That's why mostly semiconductors are preferred. For the photocatalysis, the components which we used for water purification technology are generally what is photocatalyst? Photocatalyst is the core functional component, typically a semiconductor material. Example comes titanium dioxide. When it was exposed to light, it absorbs the photons and generates electron hole pairs, as I said in the last slide. The light source which we use in this photocatalysis can be from the sun or UV lamp. The light must have sufficient energy to excite the electrons to the photocatalyst to a higher energy state. So this method is used for the contaminated water for filtration. The water containing pollutants such as organic compounds, bacteria, or dissolved heavy metals can be treated, and the wastewater or the harmful water can be filtered. For this process, generally, it requires a reaction chamber or filter. This component houses the photocatalyst and allows the contaminated water to pass. The design can be a simple tube or a multi-layered filter, often incorporating support materials. The support materials can be optional. Materials like carbon nanotubes, graphene, or other nanomaterials can be added to the photocatalyst to improve the efficiency. These supports can enhance electron transfer, prevent recombination, and improve the mechanical stability. These are some properties or characteristics of the good photocatalyst. It includes the low recombination, physiochemical stability, and high light absorption efficiency, high absorption surface area, and it requires low cost and lifetime charge separation. Types of photocatalytic materials and processes. The well-known material which we use in photocatalysis is titanium dioxide. It is one of the most widely investigated photocatalytic material due to its excellent stability, low cost, and non-toxicity. The titanium dioxide generally exists in three crystalline forms, that is rutile, anatase, and bruchite, with the anatase phase being the most photocatalytically active. Its band gap energy, mostly it will be under 3.2, allows the titanium dioxide to absorb UV light, initiating the electron hole pair generation and subsequent redox reactions on its surface. However, its wide band gap limits its activity to UV light, restricting its efficiency under visible light. The other material mostly used in photocatalysis is zinc oxide. It also has a wide band gap and making it suitable for UV light absorption. Similar to titanium dioxide and zinc oxide, zinc oxide can generate electron hole pairs upon light irradiation, leading to photocatalytic reactions. Zinc oxide exhibits a high photocatalytic activity and possesses desirable properties such as biocompatibility and transparency, making it suitable for applications in fields such as biomedical engineering and wastewater treatment. The other material which we use mostly for photocatalysis is tungsten trioxide. It is a transition metal oxide with a narrower band gap compared to titanium dioxide and zinc oxide. This narrower band gap enables the tungsten trioxide to absorb a broader range of light, including visible light, enhancing its photocatalytic activity. This can be explored for various applications, including water splitting, pollutant degradation, and solar energy conversion. One more material which we used for photocatalysis is bismuth vanadate. It is an emerging visible light active photocatalyst with a band gap of approximately 2.4 eV, exhibits excellent photochemical stability and high quantum efficiency under visible light irradiation. Making it attractive for applications where utilization of solar energy is desired. It has been used in various applications such as water oxidation, pollutant degradation, and carbon dioxide reduction. And nowadays, the porous materials have promised and gained more attention due to its properties. The name of that is metal organic frameworks. This metal organic frameworks is also used as a photocatalyst because of its specific functions. In order to improve MOF structures, photocatalytic activity can be included for carbon dioxide reduction, hydrogen production, and pollutant degradation. Recent research has concentrated on incorporating photoactive components into MOF structures. Homogeneous photocatalytic process. This system is considered homogeneous when the catalyst and the reactants are in the same phase, like gaseous phase or liquid phase. For instance, there has been a lot of interest in the homogeneous reaction utilizing iron and hydrogen peroxide, ozone and photophenton systems. True phenton type is influenced by a number of factors, including pH, UV intensity, and hydrogen peroxide concentration. Their primary benefit is that they can use sunshine instead of expensive UV lights and electrical energy. The low pH levels required for the phenton process are a drawback since iron precipitates at a higher pH levels, necessitating the removal of iron after treatment. Another method of photocatalytic process is heterogeneous photocatalytic process. In heterogeneous systems, the solid or powdered catalysts are used in the liquid reaction mixture. The catalyst is not in the same phase as the reactants. For example, the heterogeneous reaction utilizing titanium dioxide by UV light has attracted a lot of attention. The heterogeneous photocatalytic mechanism involves a number of oxidation and reduction activities that take place at the photocatalyst level. The heterogeneous photocatalytic process primarily begins with semiconductors, the ability to produce charge carriers. Following this, hydroxyl free radicals are produced, which ultimately cause organic molecules to break down into carbon dioxide and hydrogen gas. Coming to the morphology of this photocatalyst. The shapes and morphologies of photocatalysts range from nanoparticles and nanowires to 2D materials, planar films, 3D porous films, and intricate hierarchical nanostructures. The morphology of a catalyst, meaning its physical structure and shape, significantly impacts water purification by affecting the surface area, charge separation efficiency, and adsorption capacity. A large surface area enhances catalyst pollutant interaction and radical formation, while desirable nanostructures like nanorods or nanosheets promote the separation of electron hole pairs, preventing their recombination and boosting reactivity. Ultimately, controlling morphology allows for optimization of the photocatalytic process for more efficient degradation of pollutants. The shape and porosity of photocatalysts directly impact their specific surface area, which determines the number of available active sites where pollutants can be absorbed. Mostly porous structures can be used because it has the higher surface area and also high degree of porosity, like sponges or hollow spheres, because of having large surface area to volume ratio. This promotes greater contact between the catalyst and the pollutants, boosting the efficiency of degradation. And the nanostructures includes one-dimensional nanostructures like nanotubes and nanowires, which expose a larger surface area, facilitating higher absorption of light and interaction with contaminants. Some of the hierarchical structures include complex multi-level morphologies such as nanoflowers or hierarchical spheres can further increase surface area and create internal structure that that can be used for light trapping. And coming to the enhancement of light absorption, photocatalyst morphology can influence how effectively the material captures incoming light, which is crucial for generating electron hole pairs. The hierarchical structures, like 3D hierarchical structures, enhances the ability to capture light by scattering photons multiple times. This allows the material to utilize a broader spectrum of light, increasing the generation of charge carriers and boosting performance. The surface structure, coming to the surface structure, specific surface roughness and texture can improve light scattering and increase the overall photon harvesting efficiency of the material. The main challenge in photocatalysis is preventing the recombination of photogenerated electrons and holes, which would render them unavailable for the degradation reactions. So, morphology plays a crucial role in mitigating this. So, improvement of the charger carrier separation is required. Coming to the porous and nanostructured materials, the structural features of porous and nanostructured materials create pathways that encourage the separation and migration of electrons and holes, extending their lifespan and maximizing their availability for surface reactions. Coming to the crystal facet engineering, by controlling the exposed crystal facets during synthesis, materials can be designed to have different surface potentials on different phases. This creates a spatially separated oxidant reduction environment where holes accumulate on one facet and electrons on the other. It greatly enhances the charge separation efficiency. For example, studies on bismuth vanadate shows that certain facets preferentially acts as oxidation or reduction sites. In morphology of the photocatalyst, coming to the heterojunctions, synthesizing composites with different semiconductor morphologies creates heterojunctions that can facilitate charge transfer and reduce recombination. And the ease with which pollutants and reaction intermediates can move to and from the catalyst surface is critical for maintaining high activity. And these pore structures are having the interconnected pore channels in porous materials acts as conduits, facilitating the transport of target pollutants to the active sites and the rapid removal of reaction byproducts. Coming to the attached versus suspended catalyst. The morphology also influences the catalyst reusability. Catalysts grown as nanowire arrays on a substrate offer an advantage over suspended nanoparticles as they are easier to recover and reuse in water treatment systems. Coming to the zinc oxide, many studies on zinc oxide nanoparticles with different morphologies have demonstrated a direct link between morphology and photocatalytic performance. Researchers synthesized the zinc oxide nanomaterials using different methods, resulting in hexagonal rod-like and quasi-spherical shapes. The quasi-spherical nanoparticles exhibited higher surface area and generated more hydroxyl radicals, leading to significantly faster phenol degradation compared to the rod-like particles. This illustrates how a seemingly small change in a morphology can have a major impact on the degradation process by altering surface properties under radical formation. Coming to the defect engineering. Defect engineering in photocatalysis is the intentional creation or manipulation of the imperfections such as point defects like vacancies or dopants, like defects or planar defects in a semiconductor material to enhance its performance as a photocatalyst. These defects improve light absorption, charge carrier separation, and surface reaction efficiency by modifying the material's electronic structure, creating new energy levels or acting as sites for charge trapping and reactant absorption. Modifying the electronic structure also enhances the photocatalytic activity. Defects such as cation or anion vacancies and dopants can introduce new energy levels within the band gap of the semiconductor. This often allows the material to absorb lower energy visible light instead of only UV light. Also, by improving the charge separation, we can improve the photocatalytic activity. The presence of defects can create trap sites for photoexcited charge carriers. These traps hinder the recombination of these charges, prolonging their lifetime and increasing the likelihood that they will participate in the photocatalytic reaction. And also by enhancing the surface activity, we can improve the photocatalytic activity. The defects can also serve as active sites for the absorption of reacting molecules and for promoting surface reactions. The type of defects includes point defects, line defects, and planar defects. Coming to the point defects, the most common type includes vacancies, that means the missing atoms and interstitial atoms. In line defects, the deviations can be occurred from the perfect lattice structure along a line, such as dislocations. And coming to the planar defects, defects that occur on a plane like grain boundaries or interfaces. The methods for creating these defects can be introduced through various methods like doping, chemical treatments, and physical treatments. Coming to doping, intentionally adding impurity atoms such as metals or non-metals into the host semiconductor lattice. It's called as doping. Coming to the chemical treatments, reduction treatment with hydrogen or altering the chemical ratios during synthesis. And coming to the physical treatments, high temperature annealing, ball milling, or plasma etching can also create the defects. Coming to the role of membranes. In photocatalytic water purification, membranes primarily function to support photocatalysis, separate degraded contaminants, and prevent photocatalyst loss, thereby enabling a single integrated process that combines filtration and degradation to remove pollutants efficiently. These membranes also help by concentrating pollutants near the catalyst and can provide fouling mitigation through self-cleaning properties generated by the photocatalytic process. The key roles of the membrane includes photocatalytic support and containment. The membranes acts as a physical barrier, allowing photocatalyst nanoparticles like titanium dioxide to be immobilized on its surface or within its matrix. This can prevent the cost of the photocatalyst from being lost in the treated wastewater. The membrane's pore structure can physically separate suspended particles and dissolved pollutants from the water, while the integrated photocatalyst degrades the pollutants at a molecular level. The concentration and enhanced reaction. The membrane, by holding the pollutants at the catalyst surface, the membrane effectively concentrates them, increasing contact time and allowing for more efficient breakdown of the reactive oxygen species generated by the catalyst. The photocatalytic activity can degrade foulants on the membrane surface, leading to self-cleaning properties that reduce pore blocking and prolong the membrane's lifespan. Coming to the process integration efficiency. By merging the membrane filtration and photocatalytic degradation into a single unit, the process reduces the need for separate equipment, saving space, time, and energy consumption. We can also use the support materials to enhance the photocatalytic activity. This support plays a critical role in photocatalysis for water purification by immobilizing the photocatalyst, preventing its loss in the treated water and often enhancing its performance. This approach overcomes the major challenge of separating and recovering the fine photocatalyst powder after treatment in a slurry system. Coming to the immobilization and easy recovery of the photocatalyst, it includes immobilizing the photocatalyst on a solid support eliminates the need for expensive and often inefficient post-treatment steps to remove the catalyst particles from the purified water. And for enabling the continuous flow system, fixed bed reactors where the photocatalyst is fixed to a surface allow for continuous water flow, which is more practical for large-scale wastewater treatment than batch-based slurry systems. Coming to the charge carrier separation, we need to improve the charge carrier separation for better photocatalytic property. The supports can enhance the separation of light-generated electron-hole pairs in the photocatalyst. This is crucial because if the pairs recombine, no reactive oxygen species are formed, reducing its efficiency. Some supports like certain metal oxides and polar materials can facilitate this process and improves the photocatalytic activity. The most important thing for this photocatalysis process is the materials should have an increased surface area. Higher surface area always supports it supports such as porous ceramics or carbonaceous materials can provide more sites for photocatalyst deposition. This in turn increases the number of active sites available for contaminant degradation. These support materials with good absorption affinities can concentrate pollutants near the catalyst active sites. This improves the mass transfer of pollutants to the catalyst surface, leading to higher degradation rates. For improved stability and durability, this includes mechanical stability. The supports provide a stable foundation, preventing the loss of photocatalyst material during processing due to attrition or detachment. The supports like ceramics and certain polymers are chosen for this mechanical strength and durability. And coming to the chemical and thermal stability, the support must be chemically inert and stable under the reaction conditions to avoid degradation and maintain long-term performance. This is especially important for outdoor applications using solar energy. Coming to the recyclability, immobilized photocatalysts on durable supports can be reused over many treatment cycles, which significantly lowers operational costs. The common support materials which are used for enhancement of the photocatalysis are ceramics, carbonaceous materials, polymers, glass, metals, recycled waste materials. Coming to the ceramics, materials like alumina and silica can form mechanically strong porous membranes that filter and degrade pollutants simultaneously. Coming to the carbonaceous materials, substances like graphene, carbon nanotubes, and activated carbon offer large surface areas, catalyst deposition, and contaminant absorption. Co- Coming to the polymers, fibers and membranes made from polymers like polyethylene terephthalate provide low cost and also lightweight support options. Coming to the glass substrates include spheres and plates are chemically inert and cost effective. And coming to the metals, stainless steel and aluminum can be electrochemically treated to create textured surfaces for stable catalysis adhesion. Coming to the recycled waste materials, some innovative approaches uses recycled newspapers, plastics, and other waste as supports to reduce costs and promote sustainability. The support materials also have some challenges. That includes while immobilization offers many advantages, it also introduces some trade-offs. It includes reduced efficiency. Supported systems often exhibit slightly lower activity compared to suspended nanoparticle catalysts due to limitations in mass transfer and reduced exposure to contaminants. The deposition issues includes achieving a uniform, strongly adhered, and mechanically stable coating of the photocatalyst onto the support can be very challenging. Coming to the light penetration, the support's transparency and the thickness of the catalyst layer can affect the penetration of light to the active sites, potentially reducing the efficiency. So, coming to the future scope, researchers are continuously working on improving photocatalytic systems to increase their efficiency and viability for industrial applications. The recent innovations include visible light photocatalysts, floating photocatalysts, advanced materials, photocatalytic membranes, and point of view systems. Coming to using visible light photocatalysis, modifying the photocatalyst to respond to visible light, which makes up a larger portion of the solar spectrum than UV light, can significantly increase its efficiency. And these floating photocatalysts are inspired by the nature. Researchers have developed systems where photocatalysts are integrated into lightweight buoyant materials. This allows the catalyst to stay on the water surface, maximizing light exposure and making it easy to recover and reuse. The advanced materials include novel composite materials, are developed using substances like graphite carbon nitride, quantum dots, and metal doped oxides to enhance light absorption, improve charge separation, and increase catalytic activity. Coming to the photocatalytic membranes, integrating these photocatalysts into filtration membranes creates a hybrid system that combines physical filtration with photocatalytic degradation, offering a dual mechanism of water purification. Some of the point of use systems which have some advantages like low power, low cost photolytic purification systems are being developed for use in resource constrained areas to provide safe drinking water. This is my topic, and thank you for everyone who gave me the opportunity.
So thank you, dear Dr. Anantha Lakshmi. So
Yes,
even
ma'am.
though you are facing difficult time, so we appreciate your commitment.
Yes, ma'am.
Now I kindly invite Miss Sailaja to deliver the vote of thanks for this session.
Okay, ma'am.
Over to you, Miss Sailaja.
Hello, good evening, ma'am. Hello.
Yeah, you can continue, ma'am.
I sincerely thanks Dr. B. Anantha Lakshmi, ma'am, Assistant Professor, Gachon University, South Korea, for highlighting the real-time challenges in water purification using photocatalytic nanomaterials. Your global perspective and 30 years of experience provided invaluable insights. Thank you, participants, for your wholehearted engagement.
Thank you, ma'am. Thank you so much.
Thank you, ma'am. Thank you for your presentation. So after this session, kindly share the PPT of your presentation.
Sure, ma'am. Sure. Thank you very much for giving me this opportunity, ma'am.
Yeah. Day 3, session 2. So over to you, Miss Pranaya.
Thank you.
Yeah, ma'am. You can. Miss Pranaya, kindly introduce Dr. K. Varaprasad. Your voice is not clear.
Audible, ma'am, right now?
Yeah, it is okay.
Okay, ma'am. Thank you for giving this opportunity, ma'am, for introducing this. Good evening to one and all. It's my pleasure to introduce Dr. K. Kokarachedu Varaprasad, sir, Associate Professor at Faculty the Engineer, Y Technology and Universidad San Sebastian, Concepción in Chile. He earned his PhD in biophysical temperature sensitive hydrogel from the Department of the Polymer Science and Technology in India, and he has conducted postdoctoral research at the prestigious institution including Creighton University in USA, Schwani University of Technology in South Africa, and Universidad de Concepción in Chile. Dr. Varaprasad's research focus on biocidal hybrid nanomaterial for advanced biomedical applications. He has published over 156 articles, authored 6 books and 37 books chapter, holds 2 patents, and has an H index of 48 with more than 8,800 citations. Recognized in the top 2% of the scientists worldwide in biomaterial, nanoscience, and nanotechnology. He has also secured multiple research and grants and guided numerous students in the field of nanobiomaterial. Please join me in warm welcoming Dr. Kokarachedu Varaprasad sir.
Thank you for nice introduction, madam. Can I start my lecture, right?
Yeah, you can.
Yeah,
Varaprasad.
thank you. Yeah, thank you for giving this opportunity. First of all, I would like to thanks to my senior Professor Dr. Saraswati Garu. I know from my master's very well her. And also, I would like to thanks to the KPRIT College of Engineering. And also, I would like to thanks to the this faculty program who organized all this nice event. For everyone, I would like to thanks for them. Well, today I would like to present about my topic related to the microplastics and how the microplastics could give some problem for humans and for the earth. These things going to be I'm highlighting in my presentation. And well, you know that I think me and my senior Saraswati Garu, and we did masters and PhD in polymer science and technology. You know that polymers are associated within the different field, right? So that we work mainly in chemistry, physics, biology. We learn a lot of things in our studies, so that we also you know that all the people all the people know that polymers are associated in the different field side. That's why we are collaborated with several peoples like engineering peoples, we collaborated with the medical people, we collaborated with the astronomy department people, like different engineering people. Why we collaborated? Because of polymers, right? Why polymers are using in different kind of applications? Because the polymer have stimuli responsive properties. Mainly the polymers when used in the preparation of different kind of biomaterials, whatever we prepare new advanced materials, the polymers can play the key role. Uh, these roles mainly depending on the polymer structures, polymer molecular weight, polymer like different functionality. Due to these polymers, we can able to get advanced properties like temperature, magnetic, electric, moisture. These kind of properties we get for the biomaterials. So that based on the properties, we can able to the respective applications in the medical, automobile, like aeronautical, and other applications. That's why polymers is playing more key role in the advanced field. And we use these polymers. I think you are watching, right? My slides are moving, right? Yeah. Due to the polymer advanced properties in our laboratory, we prepare like different kind of smart biomaterials, hybrid materials in order to use the medical applications. And we work largely in the medical field like wound, drug delivery, tissue engineering, like that kind of things. And also we use biomedical applications like cancer, no, biocidal applications, cancer and antimicrobial applications, and also we work on technology applications. Why is not coming? Yeah. environmental technology applications, like we use like water purifications, like microplastic detections, this kind of thing also we work actively in our laboratory. Yeah. Before going to the topic, I would like to explain about small introduction about the polymers. Um, everyone knows right now what is a polymer. We know that the polymer are like micromolecule, which are made up of with repeating units like monomers, right? All the polymers have monomers. They form like a giant molecules, right? And there is a number of polymers. I don't want to explain all the polymers because it takes a lot of time. And I would like to explain like polyethylene and polystyrene related some of the materials. Polyethylene materials, like no polyethylene, they have classified into two types, like high density polyethylene, low density polyethylene. You can see here lot of materials, there's a lot of materials, this lot of materials, the different materials, so many materials is made up of with only polyethylene, high density polyethylene materials. And these materials, no, is a large, right? And if we come for the polystyrene, we can see the lot of disposable materials. A lot of disposable materials is made with the polystyrenes, like packaging applications, like food eating materials, all the things are made up of the polystyrenes. Like that, so many materials they made with the polymers. The polymers are mainly used in packaging, textile, and other medical applications too, right? And everything is good. But what is the problem to use of this problem? These polymers. The main problem: these polymers can create environmental problems. Why? Because the polymers have degradation problem. The degradation is really challenges for who work on the polymers. Oh, now I want to explain other things of polymer advantages. We can speak about later, mainly about problem of the polymers. You know that we previously we discussed here the polymers have stimuli responsive properties, right? And this is the advantage of another thing. What is another advantages we have? The other advantage is like no polymers have lightweight. Because of the lightweight, the different industries they want to use this kind of polymers in different kind of applications. And also polymer have biocompatibility, they have low cost and metals and easily design what shape you want. Like customer want like specific shape. By using a polymers, we can easily create is with less cost. That's why a lot of people in biomedicals they use like a glass, like contact lens. In the aeronautical applications, we can use like lightweight materials. And if we come for the solar applications, we can see that the polymers can use like what they say we want. That's why in different industries they interested to use the polymers in their applications. And if you go more detail in another things, like we can use the polymers in the medical applications, these polymer specific polymers, they can deliver the drugs is easily in the human body and specific pH levels. And also we can see that the polymers we can use for the stick cell applications and to protect from the snow, that kind of things, like cool weather, different kind of weathers. And also we can also like we can prepare like different kind of war materials in order to get the lightweight. The soldiers can take these materials as easily. And even if you see that like space centers like now SpaceX, like NASA, we also use like ISRO, all the people, they use the polymers to prepare their own materials. Why do we use the polymers? The polymers can very lightweight. We can take the satellites from the moon to the earth. And same thing, the cost of the things is going to be the less. That's why the automobile industries they also use the polymers. Due to using a polymers, the fuel also we can use very less also. And also the cost of the vehicle also be going to be reduced. And some of the people they also create the natural from by using of natural polymers. They also creating the food they can eatable and all the things. And also another more important is they also created. They also like a lot of countries they also created currency also with by using of the plastics. Plastics are really have more important in our daily life, right? Yeah. And we can see that like a lot of people, number of people, they use the polymers to make like packaging of food and feeding for the food for the animals. We can see that they're creating items, and also while when you make some functions, we also use different kind of plastic materials. Really, this is so amazing, right? But what is the problem for us? The problem is when you mainly this kind of polymers like this kind of polymers maybe they have less problem and but this kind of polymers they create a lot of problem. Why? These are disposable polymers. We can use only one time this kind of polymers. These polymers really create more problem for the long term using polymers. Ties, at least we can use the ties for 3 years or 4 years. It's not get much problem from the ties, but the disposable materials give a lot of problem for the humans. Why they give a lot of problems? We already discussed a lot of lot of materials they made with the polymers, right? If you go for the analysis in the okay, yeah, the lot of polymers they prepared, lot of polymers they prepared from lot of materials prepared from the polymers. When you use one time, when they broke the polymer material, what we'll do, we simply throw into the outside, right? When you throw into the outside, what will happen? They give the bigger pollution for the lands and water, and totally it will give for the problem for the air. This is really, really, really critical problem for the humans, right? And what we have to do for stopping up these things? But maybe some people think we can eat. Some people think we can burn. Some people think we can throw these materials into the oceans, and this is really do the problem for us because when you eat the polymers for animals or humans, we know that they not be digestion into the human body. And even if you go for burn the tires, what will happen? It will produce toxic air, right? And this air can going to be give problem for the humans. When you throw this kind of materials into the marine systems, and also they can give problem for the humans. Why? Because the animals they create. I think if you see in the social network, you can see the lot of things, right? The polymer is surrounding from how can I say they have tied with the animals and fishes and sea lions. This give a lot of problem for us. Then, in order to stop these kind of things, what we have to do, mindly, we have to stop to use the disposable polymers. and we can use the biodegradable polymers. And people think instead of biodegradable like disposable polymers, we can create like some kind of polymer, like paper related things, right? A lot of people, they don't know these materials also having the polymers. How polymers, they coated into the thin layer inside the polymers, like in the paper materials. And if you go for the can of the Coca-Colas and other things, also they have tiny layer of polymers inside the can or the water bottle. Suppose when you have some hot water or some other water, what will happen? The polymer will melt inside and it will give problem to the humans as well as for the animals also. Why the polymers are going to be inside into the water or any liquids, you know that the polymer is slightly degrade into the different conditions. Then the polymer can form like the microplastics. These microplastics can